space folks and space enthusiasts out there that get mad at me for saying this, but failure is an option.
This team is building a hypersonic, autonomous test plane that will go over 3,000 miles per hour.
We are pushing the envelope,
with the ultimate goal of making passenger airplanes 6 times faster than they are today.
Success is a possible outcome. Is it the most likely outcome? No. We just keep moving little bit by bit until we will this into existence.
We are in Atlanta, Georgia right now on location at Hermeus, which is a hypersonic aircraft company. They're building an aircraft which can travel 5 times the speed of sound, and I'm just like super excited to check it out. I should add, I'm super excited because I actually studied aerospace engineering in college. Yes, your typical first step to storytelling, I know. That's my voice. Yeah. Anyways, I really geek out on this stuff.
So what you see behind me is Quarter Horse. This is the first aircraft that we're building here at Hermeus, and it'll be the first aircraft to break a speed record in almost 50 years.
Hermeus' first demonstrator aircraft, the Quarter Horse, is a small single-engine autonomous vehicle designed to do 2 major things: touch Mach-5 ever so briefly to collect data, and to test their Chimera engine.
Ladies and gentlemen, meet Quarter Horse.
We're not just building one Quarter Horse in this development program, we're actually building 3. So that allows us to take that type of risk in flight tests that normally would not be possible. The other kind of key thing that enables that is the fact that Quarter Horse is autonomous. There are no people on board.
Hypersonic flight isn't new.
The X-15, forerunner of today's spacecraft and tomorrow's airplanes.
See how these planes are being dropped mid-flight from another airplane?
Really?
They're powered by rockets. That's how we've been achieving hypersonic for the last 50 years. But Hermeus is trying to do something different. Build an aircraft that can take off from sea level, hit hypersonic speeds, and land to be reused, all while using one jet engine.
The way you would design an aircraft to take off and land and an engine to do that is kind of at the opposite end of a spectrum from the optimum high-speed aircraft. You have all these different kind of constraints pulling you in different directions. So you have to make all these design compromises to get something that can both take off, break the sound barrier, and accelerate it at high speed, all in one set of hardware.
An example of this is with a high-speed aircraft like the X-15 that has a wing designed to reduce drag and increase speeds. But at lower speeds, those same features are undesirable because they reduce lift.
The actual Quarter Horse vehicle, the challenges with it are we're trying to build something as small as possible to prove out that we can hit Mach-5.
This is Danielle. She's the head engineer of Quarter Horse.
We have to be equally bad at everything. If we're really good at going fast, we'll have a really hard time going through that transonic region. We won't be able to get through it. We'll be stuck at Mach 1.2.
Supersonic flight is anything above the speed of sound, referred to as Mach 1, about 760 miles per hour at sea level. Hypersonic flight is anything above Mach 5, 5 times the speed of sound, which is about 3,800 miles per hour at sea level. Today, your standard commercial jet moves you from New York to LA at about 500 miles per hour. You guys have a landing gear because you're taking off from the ground. And that's unique.
Yeah.
You know, you're not just like dropping this from...
Yeah. Oh, it would make it so much easier if we could just
didn't have to deal with it.
Yeah, if we didn't have to land the thing, it would be so much easier.
Heat is one of the really unique challenges about hypersonic. Can you tell me about that?
We're targeting a reusable hypersonic vehicle. Our approach is to have high temperature materials so that we have what's called a hot structure.
To withstand the high temperatures of re-entry, the space shuttle was covered with ceramic tiles that could be damaged and replaced, but that kept the substructure safe. In space, there's no air, so a spacecraft is free to accelerate unencumbered by air friction. But inside Earth's atmosphere, the faster you go, the more air friction causes the surface of the aircraft to heat up. If this were in the air, traveling at Mach 5, and I were to touch it, it would be approximately
800 or 900.
800 or 900 degrees. And at the front,
the very front will be 2,000.
2,000 degrees. That's really hot.
The metal grows at those temperatures. Just heating everything up to the right temperatures is going to create load on the vehicle, and you have to be able to react.
Whoa.
Quarter Horse will be a terrible subsonic aircraft, and it'll also kind of be like a terrible hypersonic aircraft, but its job is to bridge that gap so we can get the data we need to learn so that we can actually build a really good hypersonic aircraft in the next one with Dark Horse.
Of all the challenges of going zero to hypersonic, building an engine capable of that range of speeds might be the hardest.
On a typical airplane, you'll see fuselage, our whole aircraft is wrapped around our engine.
Okay, so this right here.
This is where the engine would live.
Yeah.
The back end of it is right here, and you can see some of our thermal protection systems a little crunchy because we fired an engine in here.
A normal jet engine produces thrust by compressing air, adding fuel, igniting that mixture, and accelerating it through a nozzle. At higher speeds, a different type of jet is required, something called a ramjet.
They're an incredibly simple device. From a thermodynamic perspective, they do exactly the same thing as the traditional jet engine does, which is compress air, burn it, and exhaust it through a nozzle. Instead of having a mechanical compressor like you have on a jet engine, it actually uses a natural compression mechanism called the shock wave.
As a plane moves through the air faster than the speed of sound, air waves in front of it pile up, creating what's called a shock wave. As shock waves naturally compress the supersonic airflow inside a ramjet, there's no need for a mechanical compressor.
So really all you have is an inlet that compresses the air naturally, a combustor where you're putting fuel into the flow and burning it.
Our air-breathing propulsion is actually the entire length of the vehicle. So from the tip of the aircraft where we have the inlet section, it goes all the way to the back where we have the nozzle. So we went from idea and to building this thing in about 4 months.
4 months?
Yeah, from zero to drawings to putting the whole thing together.
Since Hermeus' aircraft will be taking off and landing from the ground, your engine needs to work as a standard jet engine and then transition to operating as a ramjet, only once at higher speeds.
The trick with ramjets is that they don't work until you're flying about Mach 2 or above. They don't get real efficient until you get to about Mach 3. So jet engines tend to work up to about Mach 2-ish. So there's this kind of gap between the two that you have to bridge in one way or another.
Hermeus argues that each of the component technological capabilities they need have been in existence for decades. The challenge is bringing them all together.
We're taking an approach that is fundamentally focused on engineering and not science. We're not inventing any new materials. We're not inventing any new propulsion systems.
Engineers are a bunch of nerds that don't like talking to other people.
Help me, what are we looking at?
So we're looking at two J85 engines. We name our engines, this is Amelia.
Amelia.
Yeah. Okay. So we're taking the core turbine section, the part that spins, to do the lower speed portions of flight. All of this comes off and we put our own afterburner on it. Yeah. It takes years and years to build one of these, and we showed in the seed round that we can take a commercial jet engine, pull off its afterburner, put our own afterburner on, and run it way higher speeds than it's designed for.
An afterburner, as the name suggests, sits at the end of a jet. It adds more fuel to the exhaust coming through the jet and ignites it, producing even more thrust and allowing the aircraft to travel at even greater speeds.
How we transition from a turbojet engine at low speed to a ramjet engine at high speed, that's something that's never been done in flight. So we'll do it in a wind tunnel on the ground, and then we'll have to do it in flight with quarter horse. That's a big risk.
All right. Whoa, this is really big.
Yeah, so this is our turbo-based combined cycle engine, Chimera.
The Chimera engine is the engine that powers it. It is designed to operate from not moving on the ground up to Mach 4 to 5, up at about 80 to 90,000 feet.
Gas turbine engine does its magic, right? Pumping the air into the afterburner during the lower speed Mach 0 to Mach 3 range. Bypass that air around. There's multiple fuel circuits. There's a flame holder in here that you can't see, but then a combustion chamber and then two clean nozzles.
So air comes in here and runs through here until you get to Mach.
About Mach 3.
About Mach 3.
Right,
And then the air passes around this and goes straight into the afterburner.
that's right. And so we dual use the afterburner as a ramjet. So it's what we call a ram burner.
I'm going to say got it because I think I got it, but that was all very, very technical stuff. You're clearly very smart, Glenn. Thank you for breaking that down for us.
You're welcome.
Hermeus has successfully tested their Chimera engine over 100 times, including for elected officials late last year.